Let's dive into this. Today, we're taking a trip. I want you to imagine we're hopping onto a quantum version of a magic school bus, taking a ride straight down the fundamental highway of reality itself. We're going to explore how abstract numbers literally generate physical particles, and we'll do it by looking at the specific geometric lanes those particles actually travel in. Buckle up, it's going to be a wild ride.
We really have to start with a question posed back in 1960 by the physicist Eugene Wigner. He wrote this incredibly famous essay about, well, what he called the unreasonable effectiveness of mathematics. Seriously, think about it for a second. Why does math, which feels like an abstract puzzle we just invent in our heads, perfectly describe the physical universe? I mean, back in 1928, Paul Dirac actually found antimatter in an equation, 4 entire years before Carl Anderson discovered it in a physical cloud chamber. The math literally knew it was there, before we did. But why?
Well, the answer we're exploring today comes from a framework called GBP. Basically says that math isn't just some map describing reality from the outside. No, mathematics represents the universe's internal consistency conditions. A particle isn't just blindly following a mathematical rule. It exists because that specific mathematical geometry is literally the only way for the universe to remain consistent. And this geometry dictates our physical constants with just, well, embarrassing precision. So our vehicle for today's journey is this incredible mathematical structure known as the Mach theta loop. You can think of this as the literal highway of reality. In the GPB framework, this exact loop perfectly predicts the masses of 55 different baryons. Those are the particles that make up atomic nuclei. And it does it with 0 free parameters. 0. That means no fudging the math, no tweaked inputs, no guesswork. The sheer geometry of this loop does all the heavy lifting.
Now, obviously, a highway isn't much use if you can only drive one way, right? This quantum highway is built on a 2-lane symmetry, which we call chirality lanes. First, you've got the C1 lane. This is the forward-propagating lane, the holomorphic part, and mathematically speaking, it pushes values up. Then, we have the C2 lane. This is the return leg, kind of like an antiphoton shadow, and it pulls values down. So they work together. It's literally like two sides of an ongoing, perfectly balanced conversation.
This brings up a crucial question. If C1 is constantly pushing up and C2 is constantly pulling down, what happens when they meet? What exactly is the compromise of this 2-lane conversation? Because they don't just fight each other forever, they reach a perfect absolute point of harmony. And the number that represents that exact balance point? Mathematicians have been staring at it for over a century. That harmonious fixed point is known as Catalan's constant, usually denoted by the letter G. It sits roughly at 0.9159. It's this 150-year-old mathematical mystery that just pops up everywhere, from quantum electrodynamics all the way to the entropy of 2D lattices. But get this, no one has been able to prove if it's rational, irrational, or transcendental. Why has it been so stubborn? Because, as the GBP framework shows us, every single prior attempt to solve it used standard analytic number theory that only looked at a single lane. And honestly, as any driver knows, you absolutely cannot understand a 2-lane highway by only analyzing one side of the road. Now, what's really interesting about this slide is this exact fraction, 15/16. To perfectly couple those C1 and C2 lanes together, you actually have to pay a toll at the edges of this quantum highway. In the Mon30 geometry that GBP uses, this fraction is known as the Noether boundary correction. It naturally arises from the prime numbers 3 and 5 at the very edge of the lattice. It is the exact mathematical toll booth required to physically close the loop. And here is the beautiful payout of paying that toll. The GBP framework actually proves that Catalan's constant G is directly derived from this 15/16 boundary correction. When you take the core product of our C1 and C2 lanes, that alternating pushing up and pulling down, it exceeds G by exactly 16/15. So this specific toll booth mathematically connects our chirality highway directly to Catalan's constant. This mystery number isn't random at all. It's the literal physical balance of these lanes. Okay, let's change our perspective for a second. If you imagine looking out the window of our quantum bus right now.
These are the landscapes of pure thought. Here, equations take form, and the Riemann Hypothesis is the greatest riddle of them all.
We can actually translate these math equations into physical 3-dimensional shapes. The balance of the C1 and C2 lanes isn't just some abstract algebra equation stuck on a chalkboard. It maps perfectly onto some of the most fascinating topological shapes we've ever discovered. Just picture these structures. In low-dimensional topology, the volume of a shape called the Whitehead link, which is basically a plane torus linked with a figure 8,
is exactly 4 times Catalan's constant, or 4g. And then there's the Borromean rings. That's 3 interlocked rings where if you remove just one, the others instantly fall apart. Its volume? Exactly 8g. Guys, this is not just a math coincidence. In our framework, the Whitehead link literally represents the photon-vacuum coupling, and the Borromean rings represent a 3-armed baryon Y junction. Particles are actually taking the shape of these rings.
And this brilliantly illustrates exactly why G shows up here. In topology, the minimal volume for shape called a two-cusped hyperbolic 3-manifold is exactly 4G. Okay, I know, that is a massive mouthful of jargon, but don't let it scare you. What are those two cusps? They literally correspond to the off-ramps of the C1 and C2 lanes of our Mach theta highway. The value 4G is just the geometric cost of closing the Mach theta loop once in 3D hyperbolic space. Topology and particle physics are telling the exact same story.
So we have particles, we have cool topologies, and we have fundamental constants. But where does this quantum highway ultimately lead us? I mean, if Catalan's constant is the fixed point of this geometric loop, does it connect anything else? Well, it turns out our little bus ride is heading straight toward the single greatest unsolved problem in all of mathematics.
Welcome to the Mertens function. You can think of it as a running tally of individual mathematical contributions, specifically something called the Mobius function, which assigns a +1 or -1 based on prime factors. Honestly, just think of it like a bank account that's constantly adding and subtracting $1. Now, there is a known ironclad rule in mathematics here. If the Mertens function does not grow out of control, meaning if its growth is strictly bounded, then the famous Riemann hypothesis is inherently provably true.
Let's move to and see how this builds, because this is where all the pieces completely snap together. Step 1. Our C1 and C2 lanes maintain an exact mirror image balance on the mod 30 lattice. Step 2. Because every single C1 prime is paired with a C2 mirror, their +1 and -1 contributions to the Mertens function perfectly cancel each other out, preventing any runaway growth. Step 3. This flawlessly balanced cancellation acts as a direct, numerical witness proving the Riemann hypothesis.
And guess what? Catalan's constant is the star witness. G isn't just some random number that happens to pop up in quantum mechanics. It acts as the actual finite certificate proving this balance exists. Think about it. If the C1 and C2 lanes weren't perfectly balanced, the math would just diverge to infinity. The absolute fact that Catalan's constant converges beautifully to 0.91596 is the numerical proof that the Mertens function cannot run away. It's literally the fixed point that holds reality together.
Which brings our journey beautifully full circle, right back to Eugene Wigner's thought about the unreasonable effectiveness of mathematics. As the GBP framework puts it, the universe is consistent. Mathematics is simply the language of consistency. That is exactly why they agree. The mass of a proton, the shape of a Whitehead link, and the truth of the Riemann hypothesis, they are all just different reflections of the exact same geometric loop.
So, I want to leave you with this provocative final thought. When we do mathematics, are we just inventing abstract puzzles in our minds? Or are we, lane by lane, highway by highway, uncovering the universe's actual source code? Really think about that the next time you look at a simple math equation. Thanks for joining me on this explainer, and hey, keep exploring.